In this example, we are going to use the Liebman method, which is using the Gauss-Seidel method to solve the PDE. So in this PDE, we have the heater plate, and the temperature is given at the boundary. So we are going to use the over relaxation with a value of 1.5. So you should know that the lambda is 1.5. And also we are going to iterate the accuracy up to the stopping criteria when the approximate percent relative error, okay, the magnitude of it less than 1%, then it will stop. So by using the Gauss-Seidel method, first of all, we assume the temperature at all of these 9 points is equal to 0. And you have to define your axis. So let's define here to be x axis, okay, or the I, and here to be the y axis, which is the j. So by using the previous numerical modeling, we can predict the temperature distribution at this 9 points by using this equation. So first of all, we want to find the temperature at point 11. And by doing this, we are going to need the point for 21. So this one is 0, 1. This one is 1, 2, and this one is 1, 0. So when you substitute I and j to be 1, 1, then you can find this number. Right? So from here, okay, we are going to obtain this equation. So in simple, it will be just the temperature around. For example, if you want to find the temperature at this point, you need the temperature beside. So the temperature 21 is here, which is unknown. Okay. So in this case, since we assume all the temperature from T11 to T33, so for all the 9 temperature is 0. So we just let T21 to be 0. Next, we have the temperature on the left hand side, which is T01. So for the T01 is equal to the temperature here. So this is the given boundary condition, which is 75 degrees Celsius. We continue with T12. So at the top, right? So the temperature is unknown, so it's based on the previous assumed temperature, which is T12 is equal to 0 here. Next one is a T10, which is here. So this temperature is equal to the boundary condition here, which is 0. After you substitute, you should be able to obtain 18.75 degrees Celsius. Then we apply the over relaxation formula, where you substitute the lambda equal to 1.5. The temperature O and the temperature nu can be found from here. So initially we say that we assume all the points is temperature is equal to 0. So therefore your temperature 110 is 0. Then after you do the calculation, you obtain the temperature here, 18.75. So this is the new temperature, 18.75. So after you substitute, you compute, you get the answer. And this answer is for the first iteration solution. So we continue to find the temperature at the second point. T21 by using the same formula earlier. So basically it's just to find the temperature all around. Right, which is the T at the top is 22, at the bottom is 20. Okay, 20 here is 0 degrees Celsius, so we can substitute with 0 plus T11. So T11 you have found earlier, so you find from the previous example, and then T31. So T31 is unknown, so initially we assume it to be 0. So this one is 0 as well, divided by 4. Right? So you can see that the previous example we have a 28.125. Right? So which is obtained from here. So after you substitute everything, you get your temperature to be 7.03. Then you apply the over relaxation. So initial the assumption temperature at all the points 0. So your TO is 0. The lambda is 1.5, lambda 1.5. The temperature, okay. So there's a typo here, so it should be T21. Right. So this is our new temperature for T21, and then you substitute here. So after you calculate using this formula, you get around 10. So you continue the same procedure for T31. So you need the information here. Okay. Then at the bottom is 0. So this one is 0. And the temperature here is 50, okay, for T41, so we substitute for 50, and the T21 can be found earlier, 10.54, so we substitute it here, and the T32 is unknown, okay, which is initially assumed as 0 in the Gauss slider. So after you substitute, you get the answer. Okay, so you should recognize from here your T320. Okay, initially we assume it starts with 0. So this is our initial guess. So after you apply the numerical method, you get the new solution, which is this. So by substituting inside this formula, you get the answer to be 22.7. So if you keep continue, we can obtain the temperature here, okay, for the rest 6 points. So without the iteration, initial guess, okay, at all the temperature point here is 0. Then for the first iteration, previously we were able to obtain these 3 temperatures. So if you continue, you will obtain the rest. Okay. So for the first iteration, when we compute the error using the percent relative error, so basically you need to find the percentage by using the current estimation. Okay, the current estimation minus the previous. So the current estimation now is 28.125. So the previous one is 0 here, divided by 28. So you can see the error is 100%. So 100% for the 1 is here, right? When we compare, we should compare like this. Okay, so if you continue for all the calculation, you will find that all point has 100% error. So we cannot stop because our stopping criteria, it should be less than 1%. So we need second iteration. So this is the first iteration result. Okay, so if you apply the limit method and also the over relaxation, so for example at this point, so T11 is equal to, this point is 75, so this point is 0. So 21 and 12, okay, can be obtained here around 10.547, 688 plus this 38.67188. So divided by 4, right? You should be able to obtain 31.05469. So we have find the temperature T11 by using the temperature around it and take the summation of the temperature around nearby it, right? And divided by 4, so we get the answer to 31.05469. So you see that you have a temperature 11 in the first iteration to be 28.125. Then you continue to find the temperature again by using the Liebman method, Gauss-Seidel. So from these two, okay, this is the old temperature, this is the new temperature. So you have to substitute inside this formula. Okay. Then you compute, you should be able to get 32.51953. So same procedure is repeated for the rest, right? You should be able to obtain the answer here in second iteration. Then we want to compute the error. The approximate error for the first point, we have to refer to this data. So second iteration is the current data, and first iteration is the previous data. So you take the current minus the previous divided by the current, okay, and then you multiply 100%, you should be able to get this answer. Okay, so in this case we have 33.51953 minus 28.125 and divided by the current. Then you just need to multiply 100. You should get this. So if you want to find the error here, last point, then you take this current minus the previous one, you found that you get negative value, right? And divided by the current 67 multiplied with 100%, you found that you get negative value. So why we don't have negative value here? Because we take the absolute, right? So all the approximate error here, we take the absolute. So we just look at the positive. We just want to know the magnitude, whether it's less than 1% or not. So now we compare all the percentage here, and we found that it's still more than 1%. So we still need to continue for the third iteration. So if you continue the process, you found that at 9 iterations, only you get all the approximate error to be less than 1%. So in this case, you can say that the temperature that we obtain here is in good accuracy. So since the criteria meet the condition, stopping condition, so the iteration stops. And this is our final result. So if you check here, you can see that since the temperature here is hot, okay, so the temperature at the point nearby to it should be high as well, right, compared to the one at the bottom. So this trend makes sense. And the temperature here, 75, okay, is higher than 50 degrees Celsius here. So on the left, it should be higher than the right. So this trend is okay as well. So it means that our solution, okay, is reasonable, right. For the Laplace equation, people have proved that if let's say this condition can be met, then we will always obtain the converged solution, right? So if less than 1, it will always converge. How if it's more than or equal to 1? So in this case, it might be diverge. So what does diverge mean here? So for example, you are given a scenario here. So after even a high number of iterations that you make, you found some result like this. So if you check the result, it doesn't make sense because it exceeds the boundary condition that you set. So if you hit the thing maximum by 100 degrees Celsius, the temperature within the body shouldn't more than this temperature, right? Logically, it shouldn't be. So this is the cases where you will face when the calculation is diverge. So means the solution, the error is large, okay, it keeps increasing, and then it's far away from the true solution. So what can we do, to solve this problem? So these are the strategy. So instead of using the over relaxation strategy, we are using the under. So you can see the lambda, previously we say that if you choose 1, it's like no effect at all. So if you choose your lambda to be greater than 1, so we say that this is over relaxation. So in this case, we choose the lambda less than 1, means the under case, right? So in this case, we are able to make the non-converged system, which is the diverged system, and we make it into converge. Or in other way, so previously we just take 9 points to make the estimation. So if you found the system become diverge, what you can do is you increase more grid number, or what we say the node point. So by doing this, we can improve the accuracy as well. So these are the two strategies that we can use to improve the convergence of the solution. So this is only needed if let's say the solution that you obtain doesn't make sense.